Hello guys, welcome to Fire Workshop, and in today's video I'm going to be showing you how to perform the experiment of fixed bias circuit using an NPN BJT. For this particular experiment I'm going to be using the 2N3904 BJT. That's the NPN BJT. I'm going to be first of all showing you the design aspect for this particular circuit so that you may design the circuit for any BJT that you have. I'm also going to show you the calculations and all that stuff that you have to do on the circuit, and later on I'll be designing it in the OrCAD software. And so this is like a complete guide to the fixed bias circuit. Next I'm going to be covering the potential divider or the voltage divider by circuit on my channel, so do check that video out as well. So this will just come out after that. So without further ado, let's get started. So first of all, this is the calculation part of this particular circuit, and this is how we're going to be designing it. I've just done it on a notebook and I'm going to be explaining it to you right here. And so let's get started. So this is the particular circuit for the fixed bias configuration. You can see that the RB is connected to the base of the transistor, the RC is connected to the collector of the transistor, and it's being supplied by a single voltage source, that's the VCC. According to the datasheet of the transistor, now this is the datasheet of the transistor that we're going to be using. This is the 2N3904 transistor. I say O instead of 0, but you know that it's 0, alright? So according to the datasheet of this transistor, you have the maximum continuous collector current. The maximum collector current that this can handle is about 200 milliampere, and the beta value of this particular transistor, which is given as HFE value of this transistor, we're gonna be simulating it at near about the collector current of 110 milliampere. So we're gonna be considering these beta values. So this is like 100 to 300. So this is the range of beta values that we're gonna get out of this transistor. So I'm gonna be considering the beta value of 150 in this particular case. Okay, so over here this is how I've shown it. So the beta value will range from 100 to 300, but we'll take it about 150 because we are not sure where the beta value is lying for this transistor. So I'm going to be taking it at 150. So I advise you to just take it in this range only. The max collector current for this transistor is specified to be 200 milliampere. So at 200 milliampere the transistor will of course it will just get really hot, because there's just going to be a voltage drop across the collector emitter path, and therefore you do need the heat dissipation for this transistor. You need to attach a heat sink or something like that to this transistor. So to avoid those things, we're going to just limit the collector current to about 10 milliampere. And obviously this is just a test circuit. This is not a fully fledged amplifier, so let's just consider the maximum current that it can handle, the maximum collector current of 10 milliampere. So this is the maximum collector current that is going to be present on our load line. And if you don't know the load line, so it looks something like this. If you draw the output characteristics, so this is your collector current and this is your collector emitter voltage. So right here we are going to consider this current right here to be 10 milliampere. So according to the beta value of 150 and the VCC, that's the supply voltage, we are going to be taking at 15 volts. And the maximum collector current I've already specified at 10 milliampere. So at Q point, your VCEQ, that is the collector emitter voltage at the Q point. Now the Q point of this circuit will be exactly at the middle of the load line. So at the middle of the load line, the VCE, the collector emitter voltage is going to be 1/2 the supply voltage, and the collector current is going to be 1/2 the maximum current that this transistor can take. So somewhere over here. So right here, if you just consider, so this is just gonna be, so for example x comma y, so x axis we have the voltage, so that is gonna be 7.5 comma 5. So this is gonna be 5 milliampere, 7.5 volts. So this is what we have done. So the maximum, so at the Q point we are gonna get 7.5 volts, and at the IC the collector current we are gonna get as 5 milliampere. Accordingly, now according to these particular values, we are gonna calculate the resistors that we need to attach to the collector and the base of the transistor. So this is the VCC. So now the VCC, so for the output loop of this transistor, I can see the transistor, the circuit over here. So the output loop is containing the RC, and this transistor in middle. So by applying the KCL, the Kirchhoff's voltage law, the KVL, I'm sorry, the Kirchhoff's voltage law, we can just see the VCC will be equals to ICRC plus VCE. Alright, so this is the equation that I've written right here. So this is the equation. According to that, we can just find out the RC value by just arranging this equation. And we already know the VCC, that's 15 volts, VCEQ, that's the Q point, the VCE at Q point, and the ICEQ. So that's the current, the collector current at the Q point. So the resistor value is coming out to be 1.5 kilo ohms. So the RC for this particular circuit will be 1.5 kilo ohms for the input loop. And again, now you can just see the input loop, VCC, RB, and the VBE. So VCC will be equals to IB RB plus VBE. So this is gonna be the input loop, and for the input loop we have again VCC equals to IB RB plus VBE. Okay, so according to that, we can just substitute, we can just find out the value of RB. That will be equal to the VCC minus VBE divided by IB. Now the IB, we know that the IB is equals to, or the IC is equals to beta times of IB. Alright, so this is the you already know that. So the beta times of IB, so IC is equals to beta times of IB. So we can just write IB as, we can write IB is equals to IC by beta. We can write that. So this is exactly what I've done right here. So IB is equals to ICQ divided by beta. Now the RB value can be substituted as VCC minus VBE divided by ICQ divided by beta. Now the VCC we already know is 15 volts. Now this is gonna be 0.7 volts, as we are dealing with a silicon transistor over here. We're gonna assume it to be 0.7 volts because obviously this voltage is really small. So 0.6 volts, 0.7 volts, it ain't gonna matter much. And this one, the ICQ, we already know the Q point, the current collector current at Q point is 5 milliampere. That's going to be divided by the beta value that we assume, that's equal to 150. So we have all the values, and by solving this particular by calculating this, we just get the base resistor value as 429 kilo ohms. So this is the final circuit that we are gonna be making on the OrCAD. Alright, so we are gonna take the base resistor to be 429 kilo ohms, the collector resistor to be 1.5 kilo ohm. This transistor is a 2N3904. And now let's just move on to the OrCAD software. And by the way, this is the datasheet of this transistor, and I'm going to be linking both these documents in the description box below, so do check them out. So without further ado, let's just go to the OrCAD software. So I've already opened up OrCAD. So you have to just open up the OrCAD, and we're going to go to Files and New Project. I'm just going to type in the PSpice. Now I'm going to type in for the YouTube video because obviously I've already made this circuit. You can just name your circuit anything you want. I'm just gonna hit on OK, and we're gonna create a blank project and hit on OK. It's just gonna take some time over here. Now what we're gonna do is we're just gonna click on P. That's just gonna open up this place part window. We're gonna type in the name of the transistor. That was a 2N3904. 904. So we're gonna see this transistor right here. This transistor is appearing right here. So double click on it, it will get selected, and we're just gonna drop it right here. Alright, next we need the DC voltage source, so we're gonna type in VDC. Alright, so that's the DC source, and we're gonna connect the DC source right here, and we need two resistors. So R, we're gonna type in R analog is what we need. I'm just gonna rotate these resistors just by pressing R. You can just rotate these resistors by pressing the R key on your keyboard. And I'm gonna place this resistor right here. I'm gonna just now make the connections. We also do need a ground, but I'll just add it a bit later. I'm gonna connect this one over here. Gonna connect this one to V1, and this to the emitter of the transistor. This will go to the collector, and this will go to the V1. Now your V1 is 15 volts in our case, and the R2 value, as we saw from this one, the R2 value was 429 kilo ohms. You can also take it to be half a mega ohm or 0.5 mega ohm, but I'm just gonna be like precise in this value because on software we do have this liberty of being as precise as we want. So 429 kilo ohm is what I'm gonna be taking. So let's just take it to be 429 kilo ohm. This one is your 1.5 kilo ohm. Okay, this 1.5k, this is 429k. All right, and now I'm gonna connect the ground to this one. So 0 CAPSYM, you're gonna click over here and click on 0 CAPSYM. Just drop the ground right here, make the connection. Now if you're wondering how am I getting the wire, so you have to just press in the W key of your keyboard to just get the wire thing. So anyways, so this is how we just get the wire. And now this circuit is fully assembled. We're just gonna name a few parameters. For example, let's just change the label for this one to be RB so that a circuit looks a bit better. I'm gonna change this to RC, and I'm gonna change this to RC, and this one to VCC. Let's just change it to VCC. Alright, now I'm gonna go to the PSpice and new simulation profile. I'm just gonna name simulation as test 67 because I've just made many simulations of the name test. I'm gonna create the simulation, and over here, right here, we can see how we need to test this circuit. So we're just gonna go to the time domain analysis and just run this second. Like we're just gonna run this circuit for this much time only, because like 1000 nanoseconds is enough, because we just don't need to go to the plotting window and all, because we just need the voltage values, and voltage values we can get from right here. So now I'm gonna just simulate this circuit. Don't go to the PSpice window that just appears. I mean, you don't need to do anything right here, just click on V. This is how you'll get the voltages that are there on this transistor. You can see that the VCE that we took at the Q point was 7.5 volts, but it's coming out to be 8.251 volts. This is because the beta value of this transistor is not exact, and we just cannot like find out the beta value of this transistor precisely. And obviously you saw that in the datasheet we have a range of beta values. Okay, so where you can see this is a range of beta values that we can take from 100 to 300. This is the reason for not getting the exact values. Similarly, you can just find the current that is flowing through these nodes. So this is like 4.5 milliampere. So we just substitute the current as 5 milliampere, but it's just coming out to be 4.5 milliampere. And subsequently, now what you're gonna do is you're just gonna note down all the values: the collector current, the VCE, the base current, and the VBE. We're just gonna note down all the values in the observation table that you have in your practical files. And then what we're gonna do is we're gonna change the beta value for this transistor. Now stick with me and follow the steps as I tell you. So we're gonna just click on this transistor till the pink lines appear. So this transistor is selected. We're gonna right click on this transistor and just go to the edit PSpice model. Alright, so clicking on edit PSpice model will just pop up this window right here. We're gonna go to this BF, that is the maximum forward beta. Now over here we're gonna, now the maximum forward beta for this transistor is specified in the PSpice model to be 254.395. So we're just gonna change it to, first of all, let's just change it to 200. Alright, so this is how you have to change it. You don't need to touch anything else for this transistor. Make sure that you don't touch anything else. The interface for this particular one might look different on your software depending upon which version of OrCAD you're using, but this is gonna be like almost similar. So we are gonna click on cross, and it will just ask you if you want to save the changes. We are gonna click on yes, and it will just like ask you to like save the changes to this one. So we're just gonna click on save, and we're gonna click on OK. So the changes have been saved, and let's just simulate the circuit one more time. Again, we don't need this plotting window. Now you can see the VCE has increased. Okay, the Q point has just shifted up, so it is now coming out to be 8.726 volts. And similarly, you'll just see the current has also decreased. because we just decrease the beta value of the transistor. Now again, you can note down all the readings for the collector current, the base current, the collector emitter voltage, and the base emitter voltage. Just note down all the values in the practical file. Now what we're gonna do is we're gonna again change the beta value of the transistor because we need 3 sets of readings. In real life, what you usually do is you just swap out the transistors from the breadboard, but in the software we don't have the option of doing that. All the transistors, all the models are gonna be the same, so therefore we don't have this liberty of just swapping out the transistors. So we have to just change the beta value for the transistor manually. So this is the limitation of just doing this experiment on a software. I'm going to do this experiment in my lab as well, and I'll just show you how to perform this in a lab, so in my home lab only. So I'll just show you how to perform this experiment, and you can also watch my YouTube shorts that I made for the variation of the like the VCE and the beta curve and the beta and the VBE with respect to the temperature, and that's a YouTube shorts that I made. So click on the pop-up I button to view that video. That's a really good video, by the way. Now we're gonna again go to this one, the edit PSpice model. Okay, now let's just change this time let's just change it to be 300 this time. Alright, I'm just gonna click on cross, and it will just ask me if you want to save it. I'm gonna click on yes. Yes, we do need to save it. Now I'm gonna run the simulation. Again, we don't need the plotting window, and if in real life you're designing this kind of circuit, it's just better to just plot the output characteristics of the transistor first before you just design the circuit. That will give you a rough idea what the beta value of the transistor is. So make sure that you do that. I'm just like advising you, like if you become an engineer and you're just designing any kind of circuit that's just related to the transistors, it's better to just plot the output characteristics first of all, or just see the output characteristics in the datasheet of the transistor. So we're gonna click on the V. First of all, you can see the voltage now is about 7.946 and something, and the I is similarly, this is also like increased. Now you can note down these values in your practical file, and this is how we perform this experiment. I hope you like this video. If you like it, do hit the like button and subscribe to my channel. Let's just hit 200 subscribers first of all, and I'll see you guys in the next video. Peace.